These are the solutions to the quiz at the end of lesson 5.3. Now number 1, it's C, and that's just Newton's law. Number 2, we have B, then C, and then A, which equals 0, so that is option B. Now number 3, I'm just going to sort of talk through how I worked out this one. So you probably might have done it just intuitively, but this is how I'll work through it. So we have F is mu naught L I1 I2 over 2 pi d. Now they're all equal distance apart. So we'll just say that FAB, now most of these are going to be a constant for all of them. So it's just some constant, I'll just call it K, random constant, times 150. The force between A and C is random constant times 25, because we're multiplying their currents and then dividing by the distance. So the distance for AC is twice the distance for AB, and force of B and C is going to be that random constant times 75. So this just gives you relative sizes of the three forces. So looking at wire B, it is repelled from both. So those forces have to subtract. So if it's repelled from both, we've got the total force is proportional to K times 150 minus 75. So we've got a 75 here. On A, it is repelled from one and attracted to the other, so we'll call that a minus, the 150, but plus 25, and that gives us a total that is proportional to 125. On C, it's going to be, again, the forces will be acting in the opposite direction, so we'll call one a negative, one a positive, and that gives us the total that would be relatively 50. So our relative sizes, on B we've got a 75, on A we've got a 125, and on C we've got a 50. So in order it's A, B, and C, and so that is A. Now, in this case, we have a magnetic field. Now, there's 16 banks of coils. Each one will be mu naught I n over 2 pi r. So that will be 16 times 4 pi by 10 to the minus 7 times 130, and current is large, it is 10 to the 4 amps, and then we have 2 pi times 1.7, and that turns out to be around about 2.5 Tesla, which is a very strong magnetic field. Now number 5, we've got a distance of 0.03 meters. So that's the radius of the circle. It's also the distance of the straight line, which is at a tangent to the circle essentially, the distance of that straight line from the point at the center. And we know that the total field, which will be the sum of the two, is 0. So we know that the magnitude of B1 must equal the magnitude of B2. So that gives us mu naught I over 2r for the circle is mu naught I over 2 pi r for the straight wire. So pretty much all of it cancels, and we're simply left with pi times I2. So we'll call this is the circle, 2 is the circle, 1 was the straight line. We've got pi times I2 equals I1. So I2 equals I1 over pi. So that is 2.55 amps, or 2.6. Now for number 6, we have a length of 0.65. We have N is 1400. Current is 4.7 amps. So B equals mu naught IN over L, which will be 4 pi by 10 to the minus 7 times 4.7 times 1400 over 0.65, and that comes to be 0.013 Tesla, or 13 millitesla. Now for number 7, we've got these two bars, and we know that the length of them is 0.85. We know that the separation of them is 8.2 by 10 to the minus 3 meters. We know the mass is 0.073 kilograms. Now, if the top one is levitating, it's because the forces are balanced. So we have the force of gravity, which is its weight, pulling down, and we would have the force pushing upwards. So if we have the two of them equal, and that is of course mg, which is 0.073 times 9.8, and that gives us 0.715 newtons. So we know that force equals mu naught L I1 I2 over 2 pi d. So 0.715 equals 4 pi by 10 to the minus 7 times 0.85 times the current squared over 2 pi times 8.2 by 10 to the minus 3. So that gives us, when we multiply all that, we have I squared equals 34507.5. So I equals 186 amps. So it would take a lot of current to actually levitate a bar that is 73 grams in mass.